Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Stephanie Gillane, your host. I am the Editorial Director at Data Science Central. I'd like to start our event off today by thanking Gurobi for sponsoring today's event. Gurobi is a long-time supporter of the Data Science Central community, and we are honored to have them sponsoring our event today. Today's webinar is entitled Mathematical Optimization and ML, featuring Forrester Survey Insights, to be presented by Gurobi. Before we begin, I'd like to briefly review the format of today's webinar. Today's event will be 1 hour long. We have two presenters who I'll introduce in just a minute. There will be a 10 to 15 minute Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We will be reviewing and presenting them on your behalf during the Q&A portion of today's event. I'm very pleased to introduce today's speakers, Mike Gualtieri with Forrester Research and Dr. Edward Rothberg with Gurobi Optimization. Mike Gualtieri's research focuses on software technologies, platforms, and practices that enable technology professionals to deliver digital transformations that lead to prescient digital experiences and breakthrough operational efficiency. His key technology coverage areas are AI, machine learning, deep learning, AI chips and systems, digital decisions, streaming analytics, prescriptive analytics, big data analytical platforms and tools, Hadoop, Spark, Flink, translytical databases, optimization, and emerging technologies that make software faster and smarter. Mike is also a leading expert on the intersection of business strategy, artificial intelligence, and innovation. Dr. Rothberg has served in senior leadership positions in optimization software companies for more than 20 years. Prior to his role as Gurobi CEO, Dr. Rothberg held the Gurobi COO position since co-founding Gurobi in 2008. And prior to that, he led the iLog CPLEX team. Dr. Rothberg has published numerous papers in the fields of linear algebra, parallel computing, and mathematical programming. He is one of the world's leading experts in sparse Cholesky factorization and computational linear, integer, and quadratic programming. He is particularly well known for his work in parallel sparse matrix factorization and in heuristics for mixed integer programming. Dr. Edward Rothberg has a BS in Mathematical and Computational Science from Stanford University and an MS and PhD in Computer Science, also from Stanford University. Thanks for being with us today, Mike and Ed. We're looking forward to your presentation. Mathematical optimization, aka mixed integer programming, and machine learning, ML, are different but complementary technologies. Simply put, mixed integer programming, MIP, answers questions that ML cannot. Machine learning makes predictions while MIP makes decisions. For data scientists to be effective, an understanding of MIP and when to use it is critical, as ML does not solve all problems effectively. In today's latest Data Science Central webinar, you will hear the results of the 2019 Mathematical Optimization Survey, commissioned by Gurobi and conducted by Forrester, and insights on how data scientists can use tools such as MIP to make complex decisions. You'll learn the latest trends in ML and artificial intelligence, key findings from the Mathematical Optimization Survey, how you can use MIP in concert with ML techniques, how industries are using MIP today to efficiently use resources, often resulting in time savings and millions of dollars in cost savings. All registrants will receive a copy of the 2019 Mathematical Optimization Study available in October 2019. Mike and Ed, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Hi, everyone. This is Mike Gualtieri from Forrester Research. I'm going to start, and then I'm going to turn it over to Ed. As part of our research, we're very interested in artificial intelligence, one of the hottest topics at Forrester and among enterprise clients. You, being data scientists, are right in the mix of this. So our perspective regarding artificial intelligence here at Forrester is that it's generally a force for good. There's a lot of talk about what AI can and cannot do, but we generally see it as a force for good because that's what enterprises are doing with it. They're delivering value to customers, whether they're business or consumers. And we see applications in virtually every area in every industry. It's across the board. The key, though, is that enterprises have to prioritize which AI to do, and when to do it and how to do it to be leaders in their industry. And so a lot of what our research is focused on is what they should do. And that led us to looking at machine learning and other intelligence technologies such as mathematical optimization and figuring out, well, how do these two things relate? AI is growing. The number of companies saying no to AI is on the decline. The number saying yes is up there. When we ask a question like this, we don't define what we mean by artificial intelligence, but this is generally in line with other surveys, with more than half of enterprises reporting they're doing something with AI. But even at that, they're largely just dabbling. We haven't really begun to see all the use cases that are actually possible. There's been some confusion about artificial intelligence and what does it mean and what doesn't mean. I think a lot of the enterprises implementing AI, they understand the difference between pure AI and pragmatic. It's much narrower in scope, but many, many use cases. And the way we advise our clients to find those use cases is to look at their business processes, look at their customer experiences. And if you think of a major corporation, there's many business processes, many customer experiences. So there's quite a few use cases, and data scientists like you are the ones who are going to make this happen because the most popular AI technology is machine learning models, and data scientists generally will create those machine learning models to make predictions. We'll delve into that a little bit more. But they have to have the right tools. And they have to have the complete tool set. And so we analyzed this very carefully, and we said, well, okay, yeah, there's all the Jupyter notebooks, and there's different machine learning tools and libraries. But what do they need to actually make those decisions, automate actions, and augment intelligence within AI applications? So obviously, the first technology, which you are all intimately familiar with, is machine learning. And generally, machine learning, specifically supervised machine learning algorithms, they're making predictions. I suppose you could say that unsupervised is also about predicting clusters and groupings and so forth. But generally, machine learning algorithms analyze that data, historical data, to make a prediction about something consequential, something like what a customer may want to use or buy next, when a machine might break down. And machine learning algorithms, they train the model, as you know, takes those inputs, it figures out what those input variables should be from, a cast of hundreds, sometimes thousands, creates that model, makes that prediction, and of course it's probabilistic, right? So we asked in this survey we did with Gurobi, we asked this question here: which of the following use cases, applications, scenarios are you planning to use or currently use? So you can see improve efficiencies. That's pretty interesting, actually, because a couple years ago, a lot of it was focused on customer insights, and you can see that shows up here. But automation, IT, efficiency operations, people are seeing use cases there, but it's across the board. And 3 years ago, when we asked questions similar to this, innovation was at the top, right? So this is actually really good news for AI technologies, because it means companies now see the benefit, not just as this pie in the sky thing for innovation, which it still can drive, but also as a routine technology for improving efficiencies and automating. A lot of the use cases, and I'm sure you're implementing many unique and different use cases. Just a quick survey of these use cases, and we're going to look at these too in the context of mathematical optimization later. Companies are using it to predict supply chain issues where there's time to do something about it, right? So enormously valuable, right? If you can predict a supply chain issue because there's implications for the customer. It's being used to detect and predict who might launch a cyber attack, when and on what systems. Again, a prediction. Life science companies are. I think this was a novel one. At least I hadn't thought of it. But when you're doing drug development, there's many possibilities and experiments, and you generally have to perform those experiments sequentially. You can parallelize some of them, but it's a physical activity. So some people are using machine learning models to predict which experiments are more likely to prove the hypothesis to avoid wasting time and to come to a compound quicker. Certainly used in IoT. You know, if a production line comes down, there's all kinds of implications to customer deliveries, just to cost. So this is probably the most popular use case in the world of IoT. People are using it to predict eligibility fraud. They're using it to determine when maintenance is needed. In this case, it's a combination of computer vision, drones, inspecting pipelines, and using it in financial use cases. I mean, this is just an example. These examples are just many examples of the literally hundreds of potential use cases. And again, most enterprises are just dabbling. And the customer use cases is also there. You know, as data scientists who do machine learning, you understand the challenges of this. And I think it's really important to think about these challenges. I mean, you live with the challenges, but I want to think about these challenges too, because as we answer this question, what is the perfect AI team? We need to understand those challenges. And, you know, the first one is really prioritizing those list of use cases. And that means that business problems have to be translated into a set of predictions. Companies are getting a lot better at this, right? Because if you go to the business and you say, oh, you know, we want to use AI, freeze like a deer in headlights, right? But when you tell them this actually translates into a prediction, okay, now they can start talking to you about what they might want to predict about a customer, about machines, or any of these use cases. And the other stated problem is the garbage in equals garbage out problem. These models are not algorithm driven as much as they are data driven. Algorithms get all the press, but US practitioners understand that data matters the most, and that continues to be a perennial challenge. And it can also be very slow without the right infrastructure, and it can be slow in multiple dimensions. It can be slow because the data sets are big, and there's typically many iterations. If it's deep learning, it may require special infrastructure. And then when you're doing things like hyperparameter tuning, whoa, I mean, the number of iterations, you really have to start to make some decisions about how many of those you're going to do. So that's becoming an increasingly challenge, especially with deep learning, but classical machine learning as well. And the other challenge with machine learning models, I guess I've been talking cavalierly about how machine learning models can predict something, but they're probabilistic, right? So that is a big challenge. The model has to have a probability that is high enough to be valuable in the use case, right? And this is why it's pretty easy to use it for ads. because no one dies if you serve them the wrong ad. And then there's the range in between. And just because you want to predict something, data may not exist. And of course, these models are based upon correlation, probably not causative, not that that matters for these use cases. That's not the goal. And the other problem is actually deploying these things in production. Models are trained on historical data, and they have to learn from experience because the past isn't always indicative of the future, so they have to be retrained. So typically when a model is deployed, highest business value, the maximum business value comes from day one. Sometimes, not always, some people say, oh, models always have to be retrained, but there are situations where in a steady state environment they may not have to be, but typically they do. They have a shelf life. So they have to be monitored in production for efficacy. That's not what IT and technology and enterprises are used to. They're used to developing code, Java code or Python, whatever, that's discrete, that is not probabilistic, and it will run as written. They may have bugs. Models have to be retrained. You may also want to remodel to increase accuracy, to use other data. So this is a continuous process too, and that's another big challenge as well. So we have to figure out ways of overcoming these challenges, especially at scale, right? Because if you're doing a few use cases here and there, that's fine. You can, you may be able to use swivel chair collaboration, like in the old days of software development, to do some of this, but it's certainly not scalable. Now, on the other hand, if we look at the other side of this equation, which I'm calling MO, just for symmetry with ML, mathematical optimization, it's a very different technology tackling a very different problem. Mathematical optimization determines the best decision based upon real-world constraints. So this is part of that, the balance to understand. Machine learning, prediction, mathematical optimization is about decisions based upon real-world constraints. So similar to what machine learning does, mathematical optimization uses some constraint functions defined by the business requirements, how much money you have, how many trucks you have, how many people you have, what their skill levels. I mean, the number of constraint functions can be a few. It can be hundreds. It could possibly be thousands. And then you have an objective of the decision. Are you trying to minimize costs? Are you trying to maximize customer service? And the solver, which is the software, that's the mathematical optimizer, that will calculate the decision and output that decision and says this is what we should do. All right? So this is very different than machine learning, which to create a prediction. So we have to understand how these two work together. In our survey, we asked data scientists and managers responsible or influence data scientists. We said, well, what are the benefits when you do use mathematical optimization? Look at that, operational efficiency, increased revenue, reduced cost. I mean, these sort of line up, right, with a lot of the machine learning ones as well. But you may notice if you download this and go back to those slides, the categories for ML were sort of in the 20% range. And you can see here operational efficiency is 60%. So very often used for that, but not limited to that. Now, let's look at the use cases. I think this is, this more than anything is where we can analyze the difference in the complementary nature of these two technologies. Here's that supply chain use case. We use machine learning to predict that there's an issue while we still have time to remediate it. But then we want to decide, we want to use mathematical optimization to decide, well, what is the least costly way to reduce shipments? Just think about that, okay? Because most ML projects stop at the top. And then there's a lot of hand waving about, and granted, that's enormously valuable information to a supply chain manager. They would love to have a prediction that says, look, there's an 87% chance that we're going to have a supply chain issue with these suppliers in this region. Now they can roll up their sleeves and get to work. But taking the next step, well, what do you actually do about it, given all of the constraints from the supplier? That can be an enormously difficult problem, but it can be decided in an optimized way with mathematical optimization. So there's a beautiful symmetry between machine learning and mathematical optimization. Likewise, we can predict who launched that cyber attack. What do we do about it? Well, now we have to decide. So some banks actually literally have hundreds, sometimes more than 1,000 investigators when these threats occur. Because remember, you're making a prediction with a probability of something occurring. Now you have to decide, well, what investigators do I assign based upon the skill level for the threat predicted and other factors. So again, a beautiful symmetry between, or a collaboration between machine learning model and predicting that will something happen, and then mathematical optimization, making the tough decisions about what to do about it. Same with our life sciences. We predict those experiments, but the experiments that the machine learning predicts might be likely to succeed, some of those experiments may be much more costly to perform than others. So you're not necessarily going to take the top 10 that the machine learning model said have likely to succeed. You have other constraints. What researchers can perform those experiments, how much they cost, perfect, again, complementary use case for machine learning. And of course in IoT, every IoT application should probably use mathematical optimization because often the asset costs are huge. So you predict that failure. Well, you don't automatically say, I'm going to shut this line down. That could be very costly. It could affect customer shipments. So you have to decide based upon what's the best time to shut that line down. Again, that can be expressed as a mathematical optimization problem with constraints where we can optimize the best time to do that. And I think you get the point here with eligibility requirements. This is a variation on the investigators. Who do we assign to maximize the recovery or adjudication of this potential fraud? We predict, again, in this case, where the infrastructure maintenance needs. How do we assign those teams based upon the cost and skill? So you can see how these are extraordinarily complementary technologies and are absolutely, for the most part, required to be together for a complete AI solution. And this is a classic. Well, what's a classic is the one below. So let's forget about the prediction here for a moment. Let's just say someone has a strategy, but they have a limited cash. How do they decide to allocate that across all the investments, given some set of constraints about how much they're willing to invest in one? So mathematical optimization is used every day, perhaps every minute, just to decide a problem like this. But when you add the prediction variables in an ML model, it can be even more powerful. And this is a very classic use case for the customer issue, right? It's very naive and simplistic to say, let's just give these customers a 10% coupon, right? So you may predict that these customers have a propensity to buy, but do you just blanket give them 10%? No, you might want to decide, well, how many coupons to actually offer to maximize whether it's revenue or profit, right? You don't want to hand those out willy-nilly necessarily. Again, perfect complementary use cases. Now, just as machine learning has some challenges, mathematical optimization has them as well. And just as machine learning has to be translated into a set of predictions, business problems have to be expressed mathematically in constraints. So sometimes that can be I don't know, I guess I'd argue that's one of the largest problems with mathematical optimization is just having that mindset of expressing the problem correctly. But there's a lot of tools that make that easier. Look, this is a technology just like any other, and so the garbage in, garbage out applies as well. What if you have the wrong constraint variables? So there's a certain quality that has to go into the definition of those constraints, just as in machine learning, there's a certain data quality that's required as well. The other problem with mathematical optimization is it can be, it is very, very compute heavy. It's doing an enormous amount of calculations when the constraints get bigger. So in some cases, I think years ago, and some people abandoned mathematical optimization simply because it could not make the decision in the time needed to make the decision. So technology has gotten a lot better, but there's a lot of choices about the technology as well. Just as in machine learning, you need certain infrastructure for certain types. In mathematical optimization, you need certain software that'll be performant in the time that you need it. So machine learning and mathematical optimization are enormously natural technologies, especially for AI. And mathematical optimization doesn't necessarily get the it usually is not lumped in as an AI technology. Usually machine learning is seen, everyone says AI and ML, right? Our view is that AI is a umbrella of technologies that includes machine learning. But these two technologies together, wow, it turns data scientists to becoming people who are predicting things, so also people who can act and decide. So that's a very powerful combination that enterprises need to actually implement real AI solutions. Now, if you think of the relationship between these two technologies, most of the use cases I gave you was when a machine learning prediction determines that we have a need for a decision, right? So remember, I was like, well, the machine learning determined that this machine was going to break down. And then I said, oh, well, now we have a mathematical optimization model that determines when we should shut it down, right? So that is one use case, but there's another one as well, and that is a machine learning prediction can be used as a variable in one of the decision constraints. So one of your decision constraints could be how many workers you have that day. Well, maybe you're not sure on any particular day, so you're going to use a machine learning model to predict the likelihood of having a certain number of workers or something like that. So when you think of machine learning and you think of mathematical optimization, think about when you have challenges in the decision constraints or uncertainty in those constraints, perhaps a machine learning model can serve that. Great use case. Your company may have some operational research or an OR specific group that just does optimization. They may actually be struggling with that and would love for data scientists to pitch in there. Likewise, I think I've made the case of why data science teams should be using MO as well. Now, the other thing is that the opposite is true. A machine learning decision can be used as a feature with the machine learning model as well. So there's lots of complementary cases here. It can be used as one of the inferencing inputs. So after you've trained the model may require one of those input variables could be a decision, right? It could be one of, say, 3 or 4 variables in there. So this is the way machine learning and mathematics are complementary. Machine learning predicts, mathematical optimization decides. And together, that creates AI solutions that aren't just intelligent, but also optimize those decisions in the most intelligent way. So you've probably been trained. A lot of you, our research shows, are familiar with or use it on a regular basis, but you may not use these technologies together. We encourage you to do so. So with that, I'm going to turn this over to Ed. Ed, on to you.
Thank you, Mike. So I'll be actually taking a closer look at mathematical optimization, going into a bit more detail on what it is and how it's been used and how it could be used. So let me start actually just by defining the problem and a few terms. So when it comes to mathematical optimization, so that term is a bit of a umbrella. It actually covers a number of different technologies. So the most widely used of those technologies is something called mixed integer programming, or MIP. And what is MIP? It's quite a simple problem to state. Turns out it's quite a difficult problem to solve. But the problem statement is actually very mathematical. So mixed integer programming, you have an objective function, something that you're trying to optimize. You have a set of decision variables. These are decisions that you need to make, and you have a set of constraints. And the statement of the problem is on the right. That's a pretty mathematical statement of the problem, but the constraints and the objective they're generally pretty intuitive. So the constraints come from things that compete for resources. So you may have a budget, so a fixed amount of money, or a fixed number of machines on a factory floor, fixed number of trucks for deliveries, fixed number of workers, etc. So you have some set of constraints that limit what you can do. And then you have an objective function, which is a quantity that you want to minimize or maximize. So, for example, you may want to maximize your profit, or minimize waste, or minimize late orders. There are a number of objective functions that you may choose. And if you look at one thing that's common among optimization problems is if you look at the number of possible solutions, the number of possible settings for your decision variables, it's astronomical. So we typically talk in terms of billions or trillions of possible solutions, but that just scratches the surface. The number of possible solutions to these problems is typically, it's truly massive. It's hard to even think about the number of possible solutions. And so, given all those possible solutions, it's tempting to just, fall back on a heuristic, something that only considers a small number of different solutions. But what optimization does, what mixed integer programming does, is it is a technology that allows you to systematically explore all possible solutions to the problem. And one nice property of mixed integer programming is at any point in the solution process, you actually get both what we call an upper bound and a lower bound. So at any point, what you'll typically have is you'll have a solution, so a set of decisions that satisfies your constraints. And you'll also have a bound on the objective for the best possible solution. So you'll know the solution you have and a bound on this best solution you possibly could get. And if you let an optimization model run long enough, those converge. And so if you let it run long enough, you will wind up with a provably optimal solution, so the best solution. And so despite the fact that there are an astronomical number of possible solutions to the problem, mixed integer programming can often give you the optimal solution, or an optimal solution. So actually, let me take a look at some of the parallels between machine learning and optimization. There are actually quite a few. So the fundamental technologies for both machine learning and optimization are 50 plus years old. In the case of machine learning, some of the statistical techniques are hundreds of years old. But the use of these has only recently become quite common. And the reason is that both of them have been enabled by an explosion of available data. So enterprises are just keeping a lot more data, and an increase in computing resources. So machines have just gotten faster and more capable. So, and if you combine that with improvements in the underlying technology, you wind up in a situation now where you can solve some very interesting problems. And in fact, if you look at the applicability of the technologies, what you find is that both technologies have very broad applicability. So if we look at the set of people who use optimization, we've done tallies of the industries that optimization is used in, and I'll say more about this on the next slide. But more than 40 different major industries use optimization, and new ones are popping up all the time. So one thing that's definitely true is that optimization is a lot less visible than machine learning, than AI. And if we think about why that is, I think the main reason is that the scope of the decisions that are made in optimization applications is just a lot bigger. So optimization is used when you've got multiple complex constraints, tight interrelationships between decisions. And so, it's used for things like, scheduling sports, for scheduling factories, for assigning workers to shifts, for big sweeping decisions. And these are not typically the sorts of things that a consumer gets exposed to day to day. And so, things like speech recognition, image recognition, autonomous vehicles, these are the sort of the wheelhouse of machine learning. Optimization is more behind the scenes, big sweeping decisions. So I mentioned that optimization is used in a variety of different industries. We did a tally a few years back of all the industries that our customers are in. And this is a sampling of that. So there's about 40 industries here. The ones in red are the heaviest users of optimizations, the ones that have gotten the biggest benefit from it. And let me make this, these are categories of industries. Let me make this a bit more concrete. So here are logos from a subset of our customers. And the main thing to notice in this is that there's just an enormous variety of different companies that are making heavy use of optimization. And so, as I present these logos, these industries, these industries use lots of different things. They use ballpoint pens. Doesn't mean that they have a big impact on the industry. So what's the impact that optimization has had in some of these industries? And the reality is that there are several industries out there that have just been absolutely transformed by optimization. So the first one I want to mention is airlines. So airlines are just a perfect application for optimization. You've got a set of very valuable resources. So aircraft cost hundreds of millions of dollars. And you've got some very complex constraints. You've got flight legs you need to cover. You've got maintenance. You've got crew. There's a lot of different things going on at once. And it's also a fairly dynamic environment. So you'll have a storm. You'll have a maintenance issue, which will cause the problem to shift. And so it's not a situation where you can just, work out a schedule, deploy the schedule, and just forget about it. You actually have to stay on top of it. And airlines are one of the earliest users of optimization. The airlines started using the technology back in the 70s and 80s. And over time, the uses of optimization in airlines has grown. And now we're at a point where it's hard to find any aspect of the operation of an airline that doesn't have an optimization model behind it. Next industry we want to talk about is supply chain. So supply chain has also been really transformed by optimization. So supply chain, the field of supply chain management and using software systems to manage supply chains, it really blossomed in the 80s. There were software systems that were built and deployed at that time, and those software systems were built around rules of thumb, so basic heuristics for determining how to run a supply chain. But as MIP technology advanced, it became clear in roughly the 90s that the technology had reached a point where you could actually solve interesting supply chain problems. And now for supply chain planning, MIP is the standard technology in almost every software system that handles supply chains. Another industry transformed by MIP is electrical power. So in the US, electrical power was deregulated in the 1990s, and that one result of the deregulation is there was a need to create a market for electricity. And again, it's a complex problem. You've got a bunch of suppliers, a bunch of potential consumers, and so there was a need for some sort of technology to solve this problem, to match up the buyers with the sellers at an appropriate price. And there were various heuristics developed. There was some early experimentation with MIP. Back in 1989, the Research Institute in this space called EPRI did a study of mixed-integer programming and found that basically the technology wasn't there yet. They couldn't actually solve the realistic problems that existed. But in 1999, actually, there was essentially a switch that flipped, where MIP had advanced significantly, and it was now at a point where it could actually reliably solve these problems. And so within a few years of when it was first pointed out that MIP had reached this point, basically every grid operator in the world was using MIP to solve these problems. Last industry I want to mention is sports scheduling. So sports schedules are actually surprisingly complex. There are a lot of very complicated constraints involved in putting together a good schedule. And this problem was solved by hand for, literally for decades. It's only in the last 10 or 15 years where software was used to actually compute these schedules. But over the last 10 or 15 years, the sports scheduling has really shifted to using mixed-integer programming. Major League Baseball moved to optimization in 2004, NFL in 2007. And optimization is producing much better schedules than were available just before they moved to optimization. All right, so I've talked a bit about how optimization has been used alone. Now I'm going to talk about how optimization and machine learning can be used together. And as Mike mentioned, they're not direct competitors. They're actually solving quite different problems. In terms of how they can work together, there are actually a few different ways that we've seen that optimization and machine learning can be used together. Probably the most common is an approach where a machine learning model feeds an optimization model. So a machine learning model makes predictions, and then those predictions are used as input to the optimization model, which recommends actions in order to take advantage of those predictions. And I'll actually give an example of an application that fits that description. So another common usage model is where an optimization model actually feeds a machine learning model. And so the way this works is you will have a lot of data. You'll have several inputs to some model, and you can feed those inputs into an optimization model. So, and what the optimization model will do is we'll say for this particular set of inputs, the optimal decision is this. The optimal set of decisions is this. And so given a variety of inputs, you feed those inputs into the optimization model. For each set of inputs, it provides a set of decisions. And then you can feed that into a machine learning model. The machine learning model can then learn a relationship between the inputs and the optimal actions. So that's a second use model. And then the third use model is, so the first two I've talked about are pretty loose integrations of the technologies. So you take the output of one and use it as the input to the other. There's also some work on tighter integration of the technologies. I'll say a few more words about that shortly. So as I mentioned, first I want to talk about using the output of a machine learning model as the input to an optimization model. And the example I want to talk about is actually something called markdown optimization. This is an application that was built by a customer of ours, a company named Blue Yonder. And the objective here is if you're a retailer and you have goods on the shelf and you want to figure out how to adjust the prices of these goods in order to get them off the shelf. So you're clearing them out, you want to move them out. So you're going to use price reductions in order to increase sales and move them off the shelves. And so the question is, what's the best schedule for marking down prices in order to clear out inventory? And what are the inputs to this model? Well, retailers stock multiple items. They've got multiple stores. And if you put something on sale, it will have an effect on sales, but the effect, it's not a uniform effect. Some items, a markdown will result in a bigger increase in sales than others. Even from store to store, the same markdown on the same item may have a different effect in one store than another. And there are a number of constraints here. There's some constraints like relationships between prices on related items. So if you've got something in a 2-liter container and something in a 1-liter container, the 2-liter container should cost more. So that's just a constraint in your model. And then there are also other constraints like workload limits. You don't want to reduce the price on every item in the store on the same day. There are limits on they have to change price tags. They have to change the price in the computer system. There's work associated with changing a price, and so there are limits on how many price changes you can do in a day. And so, as I mentioned, a customer of ours, Blue Yonder, has a software system that actually recommends price change schedules for doing markdown. And what they do is they have a machine learning model that uses historical data to predict what will happen to sales volume if you change the price. So it uses historical data for each item and for each store of what happened when the price was reduced. And this model then produces predictions for every item, for every store, for multiple different price points of what the impact on sales volume will be if you change the price to that level. And then given these predictions, the optimization model will then propose a schedule for changing the prices of every item that you're trying to mark down in order to maximize revenue. And you can certainly argue, well, how accurate are these predictions? How much information can you really feed to the optimization model? Are you really getting an optimal markdown schedule? And ultimately the measure here is, what do the results look like? And so sure, there's some noise in the predictions, but they've demonstrated 5% increases in revenue during the markdown phase from using this software. And in retail, margins are very small, so a 5% increase in revenue is absolutely huge for retail. So this is a very successful use of machine learning in combination with optimization. So as I mentioned, there are also some situations where there's a tight integration between optimization and machine learning. This is actually an active research area. There's a number of research papers looking at this. I actually want to highlight one particular set of results here. So there's a group at MIT led by a professor, Dimitri Bertsimas, who's looking at a fundamental problem in machine learning, in statistics actually, which is regression. And in particular, they're looking at an important special case of regression, which is where you have you want to limit the number of factors that actually contribute to the outcome. So this is a problem called best subset regression. You're choosing a subset. You're choosing a size of your subset of the number of factors that are actually contributing. And this is a problem that's been around forever, and from very early on, it was recognized that you could state this problem as a mixed integer programming problem. But from very early on, it was also decided that mixed integer programming the technology just wasn't sufficiently advanced to be able to solve the problem. And so there have been 30 years of heuristics to solve this problem. And these heuristics, they're quite good. But they've got limitations. So there are no guarantees on the quality of the results. They can't deal with side constraints. I mean, it's a limited model. And what Professor Bertsimas and his students have found is that if you take a modern MIP solver, you apply it to this very common problem, it can find optimal solutions in seconds or fractions of seconds. And so, this is one example of how optimization and machine learning could work more closely together. As I mentioned, it's an active research area, so there will no doubt be more over time. All right, so to sum up, I want to first talk about some ingredients for success in using optimization. So I'll talk about 5 different ingredients. The first ingredient is to succeed with an optimization project, you need a problem where there's complex constraints, or their activities competing for resources in non-obvious ways. The second thing you need is data. So if you're going to optimize what happens, you're going to make decisions to optimize what happens in the future, you need some data about the current state and also the upcoming demands. So you need to be able to know what the constraints actually are. The third thing you need is a well-formed objective function. So you need to have some sense of what it is you're trying to optimize. And this sounds obvious, but it turns out it's actually surprising just how much you can learn by actually thinking about and studying what it is that you're trying to optimize. So another thing you need a data science that has the ability to basically formulate an optimization model, which really is a process of thinking mathematically, thinking systematically about what your constraints are and what your objective is. And then finally, ultimately, you need the conviction of actually being willing to sit down and formulate your problem as an optimization problem. And one thing I want to point out about this process is we hear this over and over from customers, that the process of actually thinking about the problem you're trying to solve as an optimization problem. So thinking about what the constraints are, thinking about what your objective is. So that process actually is often as valuable as the model that results from that process. So in other words, thinking through what it is you're trying to achieve and systematically thinking about, the data you need, what the true constraints are, what you're really trying to optimize, that leads to insights beyond just the output of the optimization model. So it's a valuable process. So a few key takeaways for data scientists. Oftentimes the main challenge is actually to figure out, if you're confronted with what looks like an opportunity to pull value out of data, are you confronted with a machine learning problem or an optimization problem? As we've discussed, often the answer is not one or the other, it's often both. As a result, if you look at the set of problems that you as a data scientist can solve, machine learning opens up some set of problems, optimization opens up a different set of problems. Together, they open up yet more problems. So, by adding optimization to your toolbox, it just opens up a much broader set of problems that you can address. So how do you learn more? So you can visit our website, so Gurobi.com, and there's a button on the front page. I'm a data scientist, and it lists a number of resources that you can use to get more information. We also offer a free trial of our solver, so you can go to Gurobi.com/eval, ask for a free evaluation. And if you want more information, you can always contact us, info@Gurobi.com. So thank you. I'm now going to hand it back to Stephanie, who will lead the Q&A section.
Well, Mike and Ed, thanks for that excellent presentation. We'll get started with today's Q&A session, and I want to thank the audience for their participation. We have a great many questions that have come in during the presentation, and we'll do our best to get through all of them in the time remaining. During this Q&A session, I'll leave up this screen with contact information from Mike and Ed if you'd like to contact them for a copy of the slide deck following today's webinar. Let's get started. Mike, the first question is for you. How do ML models and MO models get deployed together?
Yes, I think this is Mike. I think what's behind that question is, do these get to, there's a valid question of, do they get deployed together? Because once you create these models, they become assets and they have to be used in a production setting. Now, if these are being used more for strategic decisions, oftentimes they're used by data scientists or they're used by business analysts in a desktop. If it's a more automated decision, that means that both the machine learning models and mathematical optimization models are going to be running in real time when decisions need to be made. So the easiest way to deploy them both is expose each separately as a service. And that service can be called by an application. If this application calls first for a prediction, and then for mathematical optimization, then it will call the service for the machine learning model, and then it will call a service that's been exposed for mathematical optimization. If it's the other way around, if there's variables, then the mathematical optimization model will have to call out to get those variables. So, I think in most cases, we see them deployed and exposed separately as services that are then orchestrated by some other program. In some cases, latency matters. Like, for example, if you're making predictions, if you're doing like fraud detection, for example, credit card fraud detection, you have maybe single-digit milliseconds in which to do that. In which case, sometimes machine learning models are actually embedded in a database transaction, and that prediction gets spit out. It might be put, hope I'm not getting too technical, it might be pushed onto a Kafka queue, where another process later will use that prediction to then use mathematical optimization separately from the transaction to determine what the action is. So anyway, that's just a few of the techniques.
Thanks for that clarification, Mike. Ed, how hard is it to learn to build an optimization model?
So it's a skill. It's certainly something that needs to be learned. So a data scientist, someone with a data science background, has the background to be able to learn this skill. In terms of the difficulty of this, so I'd say it's harder than some of the more common machine learning approaches, like regression, classification, those sorts of basic machine learning techniques. But I'd say it's actually easier to learn than some of the more complex machine learning techniques, like deep learning, reinforcement learning, those sorts of things.
Oh, very interesting. Thank you, Ed. The next question that came in is from Mike. What is the best way to gather requirements from business?
Mm-hmm. Well, there's different approaches for different technologies. As I stated, machine learning is often about prediction. And so, we often walk customers through sort of a whiteboard session where it's like we're walking through a business process and we're saying, okay, at this step of the process, how are we making a decision? And is there something at that decision that we could predict to make that a better decision? Right. And now when I say decision, I haven't brought in mathematical optimization because, I think as Ed stated, a lot of decisions are made with heuristics. And in some cases, that's perfectly fine. So the next stage is, well, if there's a prediction at this stage that can make these heuristics better, is how we're making this decision using heuristics or business rules or program logic, is this decision the type of decision that could be optimized with mathematical optimization? And, so you look at that and you say, okay, are there resources, people, time, money? Is there, resources are already always limited. And are there some resources where this decision can be best made, where that's optimized? So that's essentially the process. It's walking through business processes or customer experience and asking those questions about predictions and decisions. And then you'll sort of see potentials for one or the other or both together. But one thing I would recommend right now to data scientists, any data scientists using machine learning models, ask yourself the question for those models in deployment: is there, are you just handing off those predictions, or could you actually, with existing products, is that some sort of a constraint-based decision that could benefit from optimization?
Oh, thanks, Mike. So what about deep learning models? Is there applicability there?
So I think deep learning would be, I'd say the process is the same. Now, one thing I'd say about deep learning models, the most popular application use case for deep learning model or I should say a very popular use case is computer vision. And that's because there really aren't any other good techniques besides deep learning to do computer vision. It's opened up a whole new world in terms of face recognition, in terms of surveillance activities. But again, those are making predictions about what it sees, what's in the scene. For example, there are deep learning models that are being used to look at wafers that are coming off a line for quality. So again, there could be a prediction there. You know, we've got a quality problem. So deep learning can be different for different use cases, but it's generally the same, you know, the same thinking you would use for deep learning to discover these complementary use cases.
Thank you, Mike, for that clarification. I think we have time for one last question. This is for Ed. Ed, can you use MIP to solve ML problems?
So if you look at sort of the fundamental problem that's being solved in machine learning, it actually typically it is an optimization problem. And so there are some techniques, there's some research work about using optimization to solve some of these problems. So, you know, it's at that level, yeah. I'm not sure that's really the most interesting aspect of this question. I think that maybe a different way to look at it is oftentimes people who are trained in machine learning will actually try and use machine learning to solve what are fundamentally optimization problems. I think that's actually fairly common right now. And I think that one key point here, one thing that I think that we've tried to hit on in this webinar, is that mathematical optimization and machine learning, they really are solving different problems. And the strength, you know, you can use them individually to solve different problems, but there's a lot of situations where you can use them together. So it's not really a question of whether you can use one to solve the other. It's really a question of what you can gain by combining them and being able to solve both.
Oh, thank you, Ed. And Mike, great answers to some very good questions. For those of you that asked questions that weren't answered today, we will be sending all unanswered questions to Mike, Ed, and the Gurobi team so that they can follow up with you after today's webinar. I have just a few quick announcements. Please mark your calendars for September the 24th, 2019, and our next DSC webinar, some great ways to visualize survey data and virtually any type of data. Also, today's taping will be available for on-demand viewing later today and can be found on the homepage of Data Science Central in the Webinar tab located at the top of the page. And past webinars are available on demand at datasciencecentral.com. If you haven't had the opportunity to view them, I encourage you to take a look. They provide very useful insight into a wide variety of topics of interest to our data science community. This brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions. And a special thanks again to Gurobi for their sponsorship, as well as to our speakers today, Mike Gualtieri and Dr. Edward Rothberg, for their insight into today's topic. My name is Stephanie Glenn, and I'm very pleased to have been your host for today's event. I look forward to seeing you all again on September the 24th, 2019. Have a great day.